Hello and welcome to the 28th lecture. This lecture is the area and distance problem. Okay, so as I said in the last video, we are starting integral calculus, and I talked briefly about what integration is or how we should think about it. Let me try and be a bit more specific in this class. So we have our basic operations of arithmetic. We have addition, we have subtraction, multiplication, division. There is another natural operation, which is integration, and that's what we're going to learn about now. And integration is a generalization of addition. So if we have just a collection of numbers, A1, A2, up to AP, then we can certainly add them. A1 plus A2 plus AP. That's no problem. That's easy enough. Yeah? Cool. We could actually do something a little bit more general, and we'll learn about this a lot in Calc 2. We could have an infinite collection of numbers, B1, B2, all the way up to infinity. The sequence doesn't end. And we can also add up these things. We can consider B1 plus B2 plus B3 and so on forever. And that'll actually make sense too. And we have to be quite precise in what sense that'll make sense, but it is possible to do that. An example you might know is if we take a half plus a quarter plus an eighth plus a 16th and so on, this thing ultimately makes sense, right? And this thing is equal to 1. So we can add up this infinite collection of numbers, and it's not massively different than adding up a finite collection of numbers once you have a way to make this infinite sum be meaningful. Integration is actually a fair bit different, because instead of adding up this infinite collection of numbers or this finite collection of numbers, we are adding up another infinite collection of numbers, but a bigger infinity of numbers, because there are two main kinds of infinity. There are the kinds of infinity that we can put in a list, like 1, 2, 3, 4, 5, and so on. Okay, that's called countable infinity, and there's a kind of infinity that we can't, which is uncountable infinity. And the set of all real numbers, for example, is uncountable. The set of numbers between any number A and B is uncountable. And it's not hard to show that, but it's a little bit beyond our scope. So trust me, take this as a true fact. But if we were interested in doing this, in adding up this infinite collection of numbers where the infinity was infinity of, say, the interval AB, then we wouldn't have 1, 2, 3, blah, blah, blah. We would have our numbers all parameterized, all labeled by every number x between A and B, right? So that would be like adding up f of x for every x between, say, A and B. Okay. And it turns out we can do that. And doing that is exactly integrating. And being able to do that is a crucial thing. It's an essential thing for us to build this conceptual framework, this machine, this language of calculus. And to understand the modern world, for many applications, we will need this. We will need to be able to add up all of these numbers. We need to integrate them. So that is where this is going towards. And the simplest starting point is to think about the case when f is just a non-negative function. Yeah? And if f is just a non-negative function, then it's going to turn out that integrating is the same as finding the area underneath the graph of f. So let's write about that. So this is a preamble as to what integration ultimately will be. Now let's talk about something that seems quite different, but is actually the same thing, as we'll learn going forward. So given non-negative function f, we want to find the area underneath the graph of f. So let's draw a picture. So suppose we are here from A to B. This is the graph of f. We want to find this area here. Everything above the x-axis underneath the graph. So let's describe that quantity in the language of maths. Then area under the graph is the area of this. So this means the set of all pairs x and y, where x is between a and b, and y is between 0 and f of x. That thing is all the set of points x and y here, and I've outlined here, right? Because for every x between a and b, and for every y between 0 and f of x, that describes that entire set of points. Yeah? Okay, cool. So when can we actually do this? So we want to find out how. We want to find this, find out how to calculate this. Let's do some simple examples. If we have just a constant function, then what happens to this? Then we have a here and b here, and it is just the area of this. So if the constant is c, it's just the area of this rectangle. So area is equal to b minus a times c. That's easy, no? Well, if the graph of f is a triangle, is a times b, and suppose the height is d. Let's make that d clearer. D, yeah. Then it is not hard, right? Because it's going to be b minus a times d over 2. Some of you might have this in your minds just because you remember it, but it's actually easy to see why the area of the triangle is given by this. If we turn this into a rectangle like this, right? We see that the area here is the same as the area of this triangle. Let's change colors. Area of this triangle is the same as the area of that one underneath it, right? So the area of the rectangle is just b minus a times d, but the actual triangle we're interested in, this guy here, is going to be exactly half the area of this rectangle, because these two other rectangles are also inside, and the sum of those two areas is the same as the sum of the area of this. Yeah? Cool, so this formula is pretty natural, so in that case we can do it too. Yeah? But those are the only, well, pretty much the only really easy examples we can figure out, right? So if we have a more general function f, we have a problem. We can't do this in such a simple way. So we are going to have to be a lot smarter. So I actually got into math through being a computer geek and writing computer programs alone in my bedroom for many, many, many hours, many, many years, taught me some math, got me more and more into it. And it's actually it has some similarities, because when you write computer code, you are expressing things in a language which has to be understood by this machine. You have to express things very precisely, and you have to think logically about the order in which you want this machine to do things. So I'm going to try and explain this, and I'm going to try and make I'm going to explain it as if it's computer programming tasks that you face. And that will make sense to about half of you typically who've done some coding, and for the rest of you it won't. So apologies for you who haven't done coding. It's not going to be incomprehensible, but the metaphor is going to make less sense to you than it will to the others. It's actually a good thing to do. If you're not learning any coding, please start to do it as quickly as possible. It's a very, 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 very valuable skill. It's for sure something you'll need going forward, and it connects rather well to this kind of stuff, to math overall. I would like to say it's a much simpler thing to code than it is to learn math, but nevertheless, there are some disciplines from learning to code that are very useful. So this is how I want to present our task. We are some coders who are given the task of finding the area underneath the graph of an arbitrary function that is given to us over the interval 0 to 1. Okay, and we're not tasked with finding the precise area. We're tasked to just give some kind of a ballpark answer to this. So, given non-negative function on the interval 0 to 1, we want to approximate its area under the graph. Okay, so let's draw some axes here, and we're doing it from 0 to 1. And the input to our computer program is just some graph that is given to us. Okay, and we are allowed to do stuff. We're going to find an algorithm to do stuff to that graph that's going to spit out a number ultimately, and that number is the number we'll say is the approximation of the area underneath the graph. So this is what we're going to do as a first rough attempt at it. We're going to break up this interval from 0 to 1 into 4 subintervals like this. The first one goes from 0 to a quarter. The next one goes from a quarter to a half. The next one is from a half to 3/4. That might be a very small 3 to read. Let me try and improve that. Three over 4. Okay. So this is what we're going to do. So our input is the graph, whatever it is. Say it does something like this. Yeah? And what we're going to do is we're going to check out what the value is at a quarter, and then we're going to create a rectangle like this. The height of the rectangle is the value of the function at a quarter. Yeah? And then we create another rectangle here. We can take the value of the function at a half. That'll be the height of the rectangle, and that's our guy here. The next guy, the height will be defined by 3 over 4 like this. And the next guy is defined by 1. And these blue rectangles I've just drawn here are some kind of an approximation to the actual area of the graph, right? And we can actually figure them out because it's not too hard. So area of the blue rectangles, area of rectangles is going to be what? So the first one, the base of each of these rectangles is a quarter. It's going to be 1 over 4. And then the height will be f of 1 over 4. We're given the function f. We can certainly plug in 1 over 4 inside it, and we know what this value is. So that's the first rectangle. The second one is this one. The third one is this one. Oops. And the final one is this one. That is the area of all 4 rectangles. That'll give us some number. It won't be great, but it won't be completely nonsense either. It'll give us an approximation. Yeah? So that, if you're a coder, you can tell that that won't be particularly difficult to code. It's fairly short. The input is the function f, the output is this number. You've accomplished the task, right? But let's say you accomplish this task and you give it to your boss and then they say, okay, good job, but what if I want a more accurate answer? Is there any way you can do something better? Well, you think about it a little bit, and one of the things that should occur to you is that the reason this isn't such a good answer is because I'm overcounting, and then other places I'm undercounting. Yeah. So what could be better would be to perhaps do more rectangles. Yeah. Could be to do more of them than just 4. And you could indeed do more, right? You could indeed do more. Yeah. Let's give it a go with just some specific input, which is, say, take f of x equals x squared. Yeah? And let's repurpose that bit of, now let's put it over, let's create some space because we're running out of space. Okay, we have some space. All right, so if we take our specific input of x squared, then what does the graph look like? It looks like this, right? From 0 to 1 is 1. Here it is. Yeah. Cool. And we're going to do the thing which we've worked out. We're going to cut this into 4 subintervals, like this, like this, like this. We have 1 over 4. We have, let's write it as 2 over 4, 3 over 4. I think these are getting way too small for you to see. Let me do that better. Okay, 0, 1 over 4, 2 over 4, 3 over 4, 4 over 4. Cool. And then let's create our rectangles. Like this. Like this. Okay, cool. And now let's figure out the areas of these rectangles. So I'm gonna factor out by the length of the base straight away. Yeah? So then I just have to think about the height of each one of these, right? So the first one, since this is x squared, will have height 1 over 16. Yeah? The next one has height, so this is 1 over 2, so it's going to be 1 over 4. The next one will have height 9 over 16. And the final one will have height 1. Yeah? Let's try and clean that up. Let's put it all under 16. So it's 1 over 16 plus 4 over 16 plus 9 over 16 plus 16 over 16 And that is 30 over 16, which is like 15 over 32. Okay, just to really nail this down, what this thing is this area here. So this area is 1 over 4 times 1 over 16, right? That's this area. Oops. That's this part. And this area right here is 1 over 4 times 1 over 2 squared, which is 1 over 4, and that's this guy. So all I'm doing here is I'm factoring out the 1 over 4, just to save time. Yeah? Cool. And then these other two, just like this. All right, good. So that's an answer. As you can see, it's an overestimate. It's definitely an overestimate, yeah? But it's an answer, and I have the decimal expansion of this. This is 0.4687, okay? We could also do what is called a left endpoint approximation. So this approximation was defined by taking the height of the rectangle by the right endpoint of each subinterval. If we took the left endpoint approximation, we defined the height by the left endpoint, then the first rectangle would be this guy here, completely flat. The second rectangle would be this guy. I don't know how visible this is. This guy right here. Third rectangle would be this guy. And the fourth rectangle would be this guy. Yep. We could also do that. Okay, so let's give us some notation. So this is called R4 because we are taking 4 rectangles and we're defining them with a right endpoint approximation. So the right endpoint approx with 4 rectangles. Okay, now if instead we do with the left endpoint approximation, we're going to get a different quantity. Yeah? So I'm going to kill this graph here. Let's see what we get when we get the left endpoint approximation. So the first one is just going to be 0. So we're going to do the same thing. So I'm going to write straight away L4. The base is always 1 over 4. The height of the first one is 0. Height of the second one is 1 over 16. All right? This is this height here. The height of the second rectangle defined by the left endpoint of the second interval. The height of the third one defined by the left endpoint, it's going to be 1 over 2 squared, so it's 1 over 4. And the height of the fourth one, this guy right here, defined by the left endpoint, it's going to be 3 over 4 squared, which would be 9 over 16. And so what is this? 1 over 4. And that's put it all in terms of 16. This is 1 over 16. This will be 4 over 16. This will be 14 over 16. I can put it up here. Right? So this will be 1 over 4 times 14 over 16. So that becomes 7 over 32, right? And we have the decimal expansion for this. Seven, 5. Okay. All right, so When we take the right endpoint approximation, it is an overestimate because all of these blocks are above the graph of the function, and we count this extra stuff here. So we're counting this extra stuff here, and this extra stuff here, and this extra stuff here, and then this extra stuff here. Right? And when we take the left endpoint approximation, then it is actually going to be an underestimate because all of these guys, perhaps my picture is getting too crowded to easily see, but all of these guys are underneath. Yeah? And then we are not counting everything. There are pieces here and here and here that are not being counted. Yeah? So this thing right here is an overestimate. This thing is an underestimate. That is just because of the nature of this particular graph. Later we'll learn about what kind of graphs gives over and underestimate, but don't think it's always going to be the case that the right endpoint's over and the left endpoint's under. That's completely not the case, and you can draw some pictures to see for yourself. But we see that that these answers are not massive. Well, they're about 50% apart. What many of you already know is that the area underneath the graph of x squared from 0 to 1 is 1/3, and this isn't incredibly far from that. These are not totally insane numbers. They are significantly off, but they're not completely insane. What you can also see is that if I took smaller and smaller subrectangles, then, or smaller and smaller base length of each of these rectangles, then there would be less of this stuff that is sticking up on top here, right? And there'll be less of this stuff missing. You can just see it. Let me try and show you it. So this is 1/x squared, and let's imagine we cut it up now into 8 different subpieces like this. We cut the base into 8 different subpieces, and let's take the right endpoint approximation again. So this picture really is not particularly good, but now the excess that we have is this stuff here, 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 this stuff, this stuff, this stuff. And the total area of this is a lot less than the area of that, right? So we have much less overcounting if we cut them up in smaller pieces. And if we cut up the base into even smaller pieces, it gets better and better and better. So if your boss came back to you and said, okay, thank you for this first rough approximation, can you do something better? You can say, yeah, I can do something better. I can cut it up into even smaller sub-intervals along the base, create thinner rectangles, give you a better answer. And in fact, depending how big your computer is, how much it can store, you can actually get a pretty good answer. You would cut this up into literally hundreds of thousands of little sub-intervals. You can get a very convincing answer to this question. Yeah, but you can't get a precise answer. Even if you did cut up into hundreds of thousands of intervals, you could still have functions that are so crazy that you don't even get a particularly good answer, because the stuff is changing so much on these little sub-intervals of very small but fixed small length. So we are going to be able to get around this because we are doing calculus and we have this concept of limit. But first, let's do some numerical kind of explorations of what happens if we simply do take more. Okay, so this is really stretching the space issue here. Let's put here a little table of calculations of what happens if we take the left endpoint and the right endpoint approximation for more and more intervals. So over here will be the number of intervals on the left. So we're going to take 10, we are going to take 20, and we're going to take 30. And over here we have ln, and over here we have Rn. And then let's see, so this, if we do this, it turns out that we get 0.028, and then we get 0.308, and then we get 0.316. And then here we get 0.385, and then we get 0.358, and then we get 0.350. So the left endpoint approximation, because of the nature of this particular function x squared, is always underneath. It's always undercounting, but slowly creeping up in value, getting towards the answer that we know it should have, which is 0.333333. And the right endpoint approximation is gradually coming down towards that value as it's overcounting less and less. So it's no surprise. We see these pictures. We know this is sure is going to happen, but this is how we see it happening. So we can actually get a pretty good answer to this with, or pretty accurate approximation, because it's a fairly simple function. But we want to know how to do it exactly. And that is going to be what we learn to do after I erase this board. Okay, so we're going to do this example. For function f of x was x squared on 0 to 1, show that the limit as n goes to infinity of Rn, recall that's the right endpoint approximation with n rectangles, is equal to 1 over 3. In other words, what we know the area to be. Okay, so solution. Now, what I'm about to do is notation heavy. I'm going to put quite a number of symbols on the board. And that can be off-putting to many students who've not seen this before. However, the symbols I put down are just describing the pictures I'm drawing. As always, that is what this thing is. This is the language to describe pictures. Well, not only, but amongst other things, this is a language that describes pictures. So everything that is a symbolic expression, even if it looks long or complicated, is just representing the details of the pictures I'm going to be drawing. And it will be somewhat more lengthy expressions, but it isn't actually hard. And those of you who have done some coding, it will seem somewhat familiar, because we will be having to define things recursively, one thing from the next thing, and the whole thing will seem somewhat more familiar to those of you who haven't. Nevertheless, if you haven't seen it, it still isn't going to be a topic that you have to struggle with. You might initially feel like this is way too complicated, but it isn't. It's just how it appears on first glance. If you spend time with it, you will understand it. It will seem natural. It is again just pictures, and this stuff is absolutely just pictures. There is nothing else going on. There aren't even any calculations. We're just literally drawing pictures. No? Well, okay. There'll be one little calculation, but 90% of it is just pictures. So please don't be intimidated. Don't resist this stuff. And know that this is important, because we're going to be doing this a lot. We're going to be doing this kind of thing where we're trying to understand areas and later assigned areas by breaking these up into thin rectangles and then trying to add them up. That is going to be the next week, maybe week and a half. And it'll be a big part of what you're examined on going forward. So you're going to have to get familiar with this. And the most efficient way to do that is to get familiar with it as soon as possible. Don't let there be this kind of this cloud of misunderstanding about this that just gets bigger as I keep talking about it and keep doing things more and more like this. Get solid with this, get comfortable with this, play this video again and again, do the practice homework exercises, and come to my office hour if you still don't feel like it's making sense to you. I promise you, you can understand this. This isn't as difficult as it might appear to some of you on first glance. Okay, with this said, let's just go into it. So what's our mission? Our mission is to figure out area of this guy, x squared from 0 to 1, by finding out the right endpoint approximation for an arbitrary number of rectangles n, and then we're going to let n go to infinity, because we have this power to do this. We have the concept of limit. We're not doing this with computers where we have to stop based on how big the computer is. We can actually get the precise answer because we have this conceptual machinery to go from finite to infinite. We can do this. All right, so how do we start? This is 0, and this is 1. Okay, and if we're going to cut it up into n individual subrectangles, what's the length of each rectangle, right? Because they're all equal length. So length of base, of each subrectangle well, since there are n of them, and they are all equal length, and the sum of all of these lengths is equal to 1, then it has to be that each one has length 1 over n. Because n times 1 over n is 1, right? So each one of these subrectangles have to have length 1 over n. So let's start to put them in here. So this is the first gun here. So we go from 0 to 1 over n. This is the next one. This will be 2 over n, and so on. We keep going. And the final one will actually be n over n. Okay, so later we're going to be doing this for intervals of a different length, and not necessarily starting at 0. So we're going to develop a notation that is going to work for all of those, rather than just explicitly write down what they are right now. We're going to do this with a more general type notation, and that's going to save us time going forward. And one of the first pieces of notation we're going to use is we're going to define the length of the base of the rectangles, and typically that's called delta of x. Now this delta of x is often also in itself off-putting because it's a delta symbol you haven't seen before, but it doesn't mean anything. It's nothing here. It's just the name. I could call it h. Sometimes I call it h. It's more commonly written as delta of x. It just means a small quantity of x. That's all it means. Don't get freaked out by this delta. There's nothing deep here. I could call it anything else. I could call it h. I could call it w. I could call it anything. So nothing important. That's just the name of it. So that's delta of x. And then we're going to define all of these points here. We're going to give them names. And we're going to define the leftmost endpoint as x0. And that guy, of course, in this case is 0. Okay. And then to go from the leftmost to the next one, we are adding delta of x, right? So x1 equals x0 plus delta of x. So change color. This thing is x0, and this thing is x1. This guy will be x2. So x2 is delta of x along from x1. And since x1 is delta of x away from x0, that's the same as x0 plus 2 delta of x. And so we can continue. In fact, we're going to recursively go from xk to xk plus 1 by just shifting along by delta of x. So let's write that in the language of maths. Xk plus 1 is equal to xk plus delta of x. And this is true for every k, which is 0 all the way up to n minus 1, because xn is the last one, right? is equal to 0, 1, all the way up to n minus 1. Yeah? So that thing is just writing this thing here for every one of these guys. So this defines all of these guys at the same time. Again, if you've done some coding, this seems more familiar to you than perhaps it would be if you hadn't. But again, it should be reasonable for everybody. Yeah? Because with this rule, we can start from x0, we get x1, from x1 we get x2, and so on. All right. And we also know from this kind of thing we've just noticed here that xk is actually just x0 plus k times delta of x, right? For example, x2 is just x0 plus 2 times delta of x. x3 is just moving along from x2 by delta of x, right? So that would be x0 plus 3 times delta of x. So on like this. Yeah? So these are general things that we'll use later for other intervals in other situations. Yeah? Cool. So if we want to write down the expression for the area of each one of these rectangles, let's draw the rectangles that we are figuring out. This is the first one, right? This is the second one. We're doing the right endpoint approximation. This is the third one right here, where this thing is x3, and this is the fourth one, x4, and so on. Yeah, so the general expression, and let's write it in terms of f, because later we'll be doing this for different f, is as follows. So let's write the, so let's write, so n is equal to the base times the height of the first rectangle. So delta of x is the base, and the height of the first rectangle is given by f of, oops, this is x squared. It's given by f of x1. That's the first one. That's this guy right here. Huh? Plus the next one, delta of x, f of x2. That is this guy right here. That's x2. The base is still delta of x. So the area of this second rectangle is given by this. Huh? And we continue. Delta of x, f of x3. That's the third one right here. Yeah? That's this guy. And we continue. And there are n of these. So the last guy is delta of x, f of n. Cool. Now I can factor out the delta of x. And now I want to use some notation, right? So if I factor out the delta of x, I would have this, x1 plus f of x2, f of xn. Yeah, but I don't want to keep writing this, so I hope you've seen this before. Notation. If we have these numbers a1 plus a2 plus blah, 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 ap, another way to write this, and a shorter way to write this is this expression. Okay? All this means is exactly this. This just means this. There's nothing deep here. It is just a way to save writing, to make things a shorter expression. Instead of writing this, it's a bit more slick to write this. It's a bit shorter. I have a more narrow expression. That's it. Nothing else about that. So here I have this bunch of numbers, right? And I'll use my sum notation like this, and then I can write it like this. The sum from k equals 1 to n f of xk. Cool. All right, now that I have the expression for what Rn is, now I can put the details of what these things actually are, what the delta of x is, what the f is, and what the xk is. Huh? So we know that delta of x is 1 over n. This is 1 over n. We know that f is just x squared. So the sum k equals 1 to n of xk squared. And now let's put what xk is. So xk is given by this thing, right? But x0 is 0, and this guy right here is just 1 over n. Yeah? So actually xk is k over n. So this is Yeah. Cool. And then I can do this. Now this n squared is not changing as I sum over k, so I can pull it out from the sum. So it is this thing. Cool. So if we could understand what this is, the sum from k equals 1 up to n of k squared, we are in a good shape, right? And it turns out that the formula for this thing, so known formula, the sum k equals 1 up to n of k squared is equal to n plus 1, n plus 1, that's 2 over 6. Let me check. I got that right. I did not. It is this. There we go. And this formula is something that if you are answering a question like this, you'll be given. It is not a hard formula. It's not hard to prove. We could prove it by something called induction. Some of you might have heard about, but it's beyond the scope of this particular class. So we have to accept this as just a true fact. It's a well-known true fact. It was known to the Greeks 6,000 years ago. This is just something which we accept. Okay, we accept this is true, and now we use it because we can put this thing directly into this. And then we do some algebra, clean this stuff up. So let's multiply out this quadratic part. So we're going to have 2n squared. We're going to have a 2n and a 3n. And then we'd have a 1 right here. Yeah. And this is over 6. And we can do some more cleaning up. And this is 2 into the 3 plus 3n squared plus n over 6 n to the power 3. And let's further clean that up, right? So we can factor out, we can break this up into these individual sums, and then we're going to have 1 over 3, and then we're going to have 1 over 2 times n, and then we're going to have 1 over 6 n squared. Okay, cool. And now we're in really good shape, right? Because we have this explicit expression for Rn is equal to a third plus a little bit, which is what we expect. It's an overestimate. And this little bit is definitely tending down to 0 as n goes to infinity. So we do indeed have that the limit as n goes to infinity of Rn is equal to 1 over 3. Cool. All right. But this was a fair bit of work, right? This wasn't easy. This took us a little bit. And we needed this specific formula to do it. And if we, for example, tried to do this with x to the power 3 instead of x squared, then this formula is no use. We need another formula. And we need the analogous formula when we have the sum of k to the power 3, which is a completely different formula. It's a known formula, but it's a different formula. Yeah? All right. Cool. So what a lot of you already know is that we can find the area underneath the graph of this function really easily. right? Because many of you studied calculus before, and you know that the area underneath the graph of x squared is the integral, the antiderivative, as we've learned before. So if you haven't seen this, do not be concerned. This is only for those who have, for me to explain why we are doing it this way, which is 1 over 3. So all of you will see this later. This is the fundamental theorem of calculus. This allows us to answer this question in whatever, 3 seconds, right? Instead of this work, we have this one line. Yeah? So those of you who've seen calculus before might be thinking, this is a load of nonsense. Why are we doing it? Why are we doing this complicated method when you could just teach us the fundamental theorem of calculus? Well, this is why. Because, well, there's 2 reasons. First of all, this is a game changer. This is a societal human game changer. So back in the day, back before Leibniz and Newton, there were people like me standing in rooms full of younger people like you, learning math and studying these problems, and people like me would work hard to explain how you could find the area underneath the graph of x squared doing stuff like this. And then later we'd do x to the power 3, and then we'd do other functions. And that was the best that we had to do it. That was the very smartest people around were doing it this way. And then came these guys with this really simple, really beautiful, profound idea, the fundamental theorem of calculus. And that made all of this hard work people were doing just unnecessary. It just was a game changer, a complete game changer. If you are a research mathematician before this time, you might spend years trying to find the area underneath the graph of some specific function doing complicated methods. And then comes along fundamental theorem of calculus and renders that just an exercise. And to see the full impact of this, to fully appreciate how significant this is, because it feels like just a toy, because it's just following a rather simple algorithm. To see the full impact of this idea and to fully understand what it means to be calculating the integral, then we teach you this. The book does it this way for a reason. It's the most well-used and popular book in the States for a good reason. This is the way to really drill down for students why, what is the integral, what is this problem, the area underneath the graph, why it's hard, and why this stuff, fundamental theorem of calculus, is so profoundly powerful. It's a bit like teaching you how to it's a bit like teaching you how to build a house. And if you really want to teach people how to build a house well, then you're not going to first of all give them all the power tools we have now. We're not going to give them all the very labor-saving, ease-making tools we have now. We're not going to give them your power drill on your nail gun and your laser guided lines. You're not going to do that stuff. You're going to give them a hammer. You're going to give them nails. You're going to give them just basic hand tools for them to really learn what's going on when you build a house. So it doesn't seem like magic. It doesn't feel like pressing some buttons or whatever, so that they see what's the bones of the machine of building a house. Going through this, you see the bones of the machine of what an integral is. And it doesn't become just some sort of thing where you're not even aware what you're doing and you're just doing step 1 up to step 3 and whatever. That's the first reason. And the second reason is equally important, is that this thing I've just done is actually called a Riemann sum. And it's extremely important to explain many of the future things hopefully you will learn in multivariable calculus, and you'll even learn them in calculus 2. If you look at some of my online calculus 2 lectures, I will explain quite a number of the formulas by breaking things up into little pieces and then understanding each piece and then adding them all together. That's one of the main ideas of calculus, is that on a small scale, you can understand things because on a small scale, they look linear, they look like lines. And then if you understand things on a small scale, calculate what it is, then put all the pieces together and pass to the limit. That is what we just did here. That's called the Riemann sum. So if you get familiar with this, if you get familiar with taking Riemann sums with this idea, then all of these future things really are transparent. So if you do multivariable calculus, and I really hope you all do, there is a formula every third class. No, there's two formulas every 3 classes minimum. And all of these formulas follow very easily from this thing I just described, this breaking things up into little pieces where they're linear, finding the expression where it's linear, adding them all together, a Riemann sum, and passing to the limit. It's what I call the Riemann sum machine. So if you get used to doing that, you will see all these formulas are transparent. They're easy to understand. And if you don't, then you just have a bunch of meaningless symbols in a line that could be anything, could be a pin code. So to understand the more advanced things I hope you're all going to study, you need to be familiar with this machine, with this procedure of breaking things up and adding them up one by one, and then passing to the limit. So it's going to be a very most efficient way for you to go forward in your study of calculus if you're serious about this, or even if you're not serious about it, if you just want to do decently well in the exam, is to get good with this straight away, even if it seems initially unfamiliar, even if you think there's no point because later we're going to learn a different way to do it. Trust me, this is worth getting very good at. So every time I teach multivariable calculus to students I haven't taught before, I go through this. I ask them if they recognize it, and they say no, they don't recognize it at all. But it's here. It's a Riemann sum. It's a crucially important idea. We're going to be talking about it in the next week, a week and a half. It's not difficult, and please get comfortable with this as quickly as possible. Okay, I'm going to raise the board, and now we're going to move from this area problem to the distance problem, which will initially seem disconnected, but then we'll see how it's connected, and this whole thing will hopefully start the formal coherent picture for you. Okay, let's start to discuss the distance problem. So imagine you have a car which has its odometer broken, so you can't tell how far you're going. But what you can do is record the speed at various time intervals. And let's say you do this every 5 seconds and you're recording the speed in feet per second. So let's put up a table of the things you would actually, of what recordings you might actually have. So this here is the time. And you're doing these recordings at 5 seconds, at 0 seconds, at 5 seconds, at 10 seconds, at 15 seconds, at 20 seconds, at 25 seconds, and at 30 seconds. And these are the times. So you're going 25 feet per second, then 31, then 35, then 43, then 47, then 45. Do that again. And then 41. Okay, so if we wanted to get some idea how far we're traveling, so this is speed. Well, if we had a constant speed, it would be easy, right? If we are going at 60 miles an hour for 2 hours, then we're going to go along 120 miles, right? We don't have a constant speed, which is why we are doing this. And what we're going to assume is that from 0 to 5, I mean, it's obviously changing from 25 to 31, but we're going to approximate it by 25 because 31 isn't too far from 25. And then from 5 to 10, we're going to approximate it by 31 because 35 is not that far away. And we're guessing that along that whole time interval from 5 to 10, it's really not that far from 31 feet per second. Yeah? And so on. So we're going to approximate our speed from whatever to whatever by whatever it was at the left endpoint. Yeah? So distance traveled. So we're going to multiply everything by 5, right? Let's do a proper 5. And then we're going to put the speeds here. So from 0 to 5, it's like 5 times 25. So this is the first bit of distance traveled we can calculate. And then from 5 to 10, we're assuming it's like 31. And then from 10 to 15, we're assuming the speed is well approximated by 35. From 15 to 20, well approximated by 43. From 20 to 25, well approximated by 47. And then from 25 to 30, well approximated by 45. Yeah? And if we do that, put that all together, it turns out that we've gone 1,130 feet. Okay? That's not spelling words. Speed. Okay. Cool. So that's not bad, right? That's some sort of an answer. But what if we wanted to have a better answer? Well, if you think about it for a little bit, you would conclude that if you want to have a more accurate answer, you were going to not use this approximation of 25 feet per second from 0 to 5, because that might not be that accurate. It's more likely to be accurate if we made an approximation over a shorter time period, right? So what if we cut the time periods into smaller time periods? So what if we did it every 2 seconds? Huh? If we did it every 2 seconds, right, then we would have many more recordings, right? Many more recordings of the speed, but we could do the same thing. Every recording we have, we will note it down, and then we'll calculate the total amount of distance traveled by assuming that from 0 to 2, it's like the speed we are at 0, and then from 2 to 4, it's like the speed we are at 2, and so on and so on and so on. And we will take all those speeds, add them together, and we'll divide and we'll multiply by 2, and then we'll get some number which is probably a better approximation. Yeah? And if we think even further, then we're like, okay, better would be to do even smaller time intervals. So it starts to be impractical. It's very hard to record things every 2 seconds, but imagine we have superhuman powers and we can write down things very, very fast. Then we could record speeds, say, every 10th of a second. Yeah? And that would give a better answer. But this should seem familiar. This should seem like the same kind of issue we faced before. So actually what we're doing is as follows. What we're going to plot here is the graph of the speed of the function. And so I'm not going to make a good attempt at going up and down according to these numbers, but whatever. So let's say we're doing something like this. Let's say this is the speed. So graph of the speed. And what did we do when we did this approximation? We said, okay, from 0 to 5, what we're doing is approximating the distance traveled by taking whatever speed we are at 0, and multiplying it by 5, which is the area of this rectangle. Huh? And then from 5 to 10, we are taking the height of this rectangle. Unfortunately, it's the same height according to my diagram. And again, we are taking this as an approximation, this 31 is an approximation, and multiplying it by 5, and that's going to be the area of this rectangle. Okay. This guy here, from 10 to 15, we are assuming 35 is a good approximation, so we're taking 35 and multiplying it by 5, that's the area of this rectangle, and so on. What we're doing is taking the left endpoint approximation to the graph of the speed. So the sum of all of these quantities is the same as the area of all of these rectangles. And this is just the left endpoint approximation with how many? 1, 2, 3, 4, 5, 6, 7. Right, 3, 4, 7. So this is just L7 of graph of f, where f is the speed. Yeah. And just as we discussed before, to have a better understanding, we're going to have smaller and smaller rectangles, right? Rectangles with thinner and thinner bases. And as we do that, we're going to get that the area of these rectangles is going to approximate better and better the area underneath the graph of the speed. And therefore, the exact answer to how far you're traveling is the exact area underneath the graph. So cool. So if we were in real time able to record the speed at every moment in time, and we were able to, in real time, well, maybe not in real time, but after the fact, integrate or find the area underneath the graph of that function, then we'd know exactly how far we've traveled. And okay, you might think, well, this is an artificial example. I would just fix my odometer, right? That's going to be the easier solution. And agreed, but you can imagine situations where there isn't an odometer that you can create, right? The odometer is just counting the number of revolutions of your axis, right? Multiplying it by the right number. That is not always available. So let's consider again space travel. So as I said in the last lecture, when rockets are sending these vehicles to dock with the space station, they're not being piloted, they're not being driven, they're being sent, the trajectory is being calculated to arrive very, very close. And then the last part of the journey, the last however many meters, 100 meters, perhaps there are, well, for sure, the astronauts are directing it, trying to directly connect the docking mechanism to the space station. But imagine some future time when we can actually fly the spacecraft, where we're actually directing it, right, around the place. We can choose where to go, fly it all around the place. Then how are you going to, I mean, we were doing this to a little extent already, but imagine that we were flying it for long distances and directing it on a whim to go here or there or whatever. Well, you're not going to have an odometer, right? You can't record how far you're traveling with anything because there's nothing, there's no rotating axle, there's nothing like that. What you do have is the information about your thrust, right? Your thrust in your engines. Yeah? So you know you know continually what acceleration you are adding to your space vehicle. Yeah? And therefore, as we learned last time, we go back from acceleration, we can find the velocity. So you know exactly what your velocity is second by second, millisecond by millisecond. Yeah. So if you want to find out how far you're traveling, right? Say you're going in a straight line, just directly know what distance you've gone from A to B, yeah, and you're varying your thrust, therefore varying your acceleration, and therefore varying your velocity. You would be able to integrate up your velocity function, yeah, and find out exactly how far you've traveled over some period of time. Yeah. And that is just one example. There are indeed many examples, and we'll see them later, where you have information about your velocity or about your rate of change, and you actually want to know about the total difference as a consequence of this. That, in these cases, when you have a positive function, is the area underneath the graph. So this is a natural thing that you'd want to do to understand the world. This is not just an academic example, just an academic exercise. Let's see if we can figure this out. This is of real practical value to be able to do that. And that's why. That's one of the reasons why integration is such a fundamental thing in order to understand and describe the world, as we'll see going forward. All right, so that's enough for today. Have a great day. See you all